Welcome back to the deep dive. We're so glad you're here with us today because we've got, well, a pretty fascinating mission.
Yeah, we're looking at the incredible intersection of artificial intelligence software and the raw physical hardware that actually makes it all possible.
That we're going to demystify how these massive AI models are built, why
Yeah.
graphics cards, yes, the things originally designed to render video games,
Right.
why they are the secret engine of the AI revolution.
And how new, incredibly clever mathematical techniques are democratizing AI for everyone, including you.
Exactly. And we're drawing all of this from a comprehensive 2025 textbook. It's titled GPU Accelerated Deep Learning by Ramchandra S. Mangwilkar and Plavi Vijayakavan.
It's a fantastic resource.
Okay, let's unpack this.
Mm.
When I think about the sheer scale of these modern neural networks, it almost feels like looking down at a sprawling, glowing cityscape at night.
Oh, I love that visual.
Just millions of little interconnected nodes and pathways lighting up, passing data back and forth.
That cityscape metaphor is actually perfect for today's topic. What's fascinating here is how the source text connects the deep, highly abstract math of neural networks to the physical, microscopic silicon of GPUs.
The actual hardware.
Yeah, that interconnected world of AI really is like a massive metropolis. It's a complex structure built from thousands of smaller, distinct components working in parallel.
Just like the hardware and software we're about to discuss. But before we get into the hardware of it all, I think we need to get our terminology straight for the listener.
Good idea.
The text uses this great visual of nested squares to explain the relationship between the different fields of AI.
Like a Russian Matryoshka doll.
Exactly. At the very outside, the largest square, you have artificial intelligence.
Right.
Inside that is machine learning. And then at the very innermost core, you have deep learning.
Which is just a highly specialized subset of machine learning.
But it's the one driving all the massive breakthroughs right now. And it all starts with, well, biological inspiration, right?
Precisely. Researchers as far back as 1943 were looking at the human brain to figure out computation.
That long ago.
Yeah. A biological neuron has dendrites, which act as input terminals receiving signals.
Cool.
It has a nucleus, which is basically the CPU processing those signals. And it has an axon, which is the output wire sending the new signal to the next neuron.
So a single layer neural network, which essentially performs basic linear regression, works the exact same way.
The exact same way. You have input features acting as dendrites. They get weighted and summed up in a computational node.
The nucleus.
Right. And then an activation function fires an output.
It's a really elegant analogy. But I was looking at the section on traditional neural networks, the ones called multi-layer perceptrons, or MLPs.
Right.
And the math just didn't make sense to me when it comes to images.
How so?
Well, if an image is just, say, 1 megapixel, which is a million pixels,
Yeah.
how do we suddenly end up with billions of parameters just trying to teach the machine to identify a dog?
It's a great question, and it's exactly the bottleneck researchers hit early on. The problem is that an MLP ignores the spatial structure of an image.
It just flattens it out.
Exactly. To process a picture, an MLP has to flatten it out into a single, massive, one-dimensional line of a million pixels.
Wow.
And in a fully connected network, every single one of those million pixels connects to every single neuron in the next layer.
So if your first hidden layer has just 1,000 neurons,
You're multiplying 1 million by 1,000.
suddenly you have a billion connections.
A billion parameters
Yeah.
for a tiny, low-resolution image.
Okay, so it's computationally impossible. You'd run out of memory instantly.
Instantly. Plus, flattening the image destroys the context. A pixel's meaning is tied to the pixels immediately surrounding it.
Because that's how we see edges, shadows, shapes.
Exactly. That's why convolutional neural networks, or CNNs, were such a massive breakthrough. They completely changed the approach using 3 core principles.
Which the text breaks down really well.
Yeah. First, spatial structure, they keep the image as a 2D grid. Second, locality. The network only looks at small neighborhoods of pixels at a time.
Wait, so instead of trying to learn every pixel at once, it's just passing a tiny magnifying glass over the image,
That is a great way to picture it, and that ties into the third principle, which is translation invariance.
which is just a fancy way of saying a cat is a cat, whether it's in the top left corner of the photo or the bottom right.
Right, because the CNN uses that small sliding filter called a kernel. It shares the same learned weights across the entire image.
And this weight sharing strategy drops the parameter count from billions down to just a few hundred.
It's revolutionary.
That is an incredible optimization for spatial data, like images. But what about time? Like if I want an AI to predict stock prices.
Or translate a speech as you're talking.
Right. The text introduces recurrent neural networks, or RNNs, for that. But it also mentions a dramatic flaw called the vanishing gradient. I want to make sure I understand this. A gradient is basically the directional step an AI takes to correct its errors during training, right?
Exactly. Think of a gradient as a compass pointing the AI toward the correct answer.
Okay.
During the training process, the AI looks at how wrong its prediction was,
Yep.
and it calculates these gradients, multiplying them together as it moves backward through the layers of the network to update its weights.
But if it's analyzing a long sequence of data, like a long paragraph of text, what happens to those gradients?
Well, if the mathematical values of those gradients are less than 1, and you keep multiplying them together step after step,
They shrink exponentially.
exactly. Eventually, they vanish to 0. By the time the AI tries to update the weights for the very first word in the paragraph, the gradient is gone.
So the network stops learning from earlier data.
Yeah.
It literally forgets the beginning of the sequence.
It does.
So it's basically like playing a massive game of telephone where the original message just fades into static.
That's exactly.
How do we fix that?
Researchers fixed it by introducing long short-term memory cells, or LSTMs.
Right, the LSTMs.
Think of an LSTM as having a bouncer at the door of its memory bank.
A bouncer.
Yeah, it uses specific mathematical functions to explicitly decide what information is important enough to keep, what is irrelevant and should be forgotten, and what should be passed on to the next step.
It protects the gradient from vanishing.
Precisely.
Okay, so we have all these brilliant architectures, CNNs for space, LSTMs for time, but the sheer volume of math required for any of this is staggering.
It really is.
We're talking about matrix multiplication, right? And for you listening, a matrix in this context is just a massive grid of numbers representing the AI's weights and the data it's looking at.
Right.
Why do we rely on GPUs, graphics processing units, to do this? Why not the CPU that's already in my computer?
It comes down to architectural differences. A central processing unit, a CPU, is designed like a brilliant high-speed executive.
Oh, yeah.
It executes complex tasks sequentially, one at a time, really fast. But deep learning doesn't need one complex task.
It requires millions of simple calculations.
Right, like multiplying those grids of numbers that don't depend on each other. General-purpose GPUs are perfect for this. While a CPU might have a dozen powerful cores, a GPU has thousands of smaller, simpler cores.
That can perform parallel math simultaneously.
Exactly.
The text also makes a clear distinction between dedicated GPUs and integrated GPUs.
Which is very important.
Right, if you're doing serious AI training, you need a dedicated GPU. They draw high power, they generate a lot of heat, but they have their own dedicated video memory, or VRAM.
Which prevents data bottlenecks.
Exactly. Whereas integrated GPUs just share memory with your regular CPUs, so they're budget-friendly for laptops.
But they'd choke on massive AI workloads.
They just instantly choke.
Yeah.
So that underlying hardware is the engine.
It is the engine.
Right, but we've got the hardware engine built with GPUs,
Right.
and an engine is useless without a steering wheel.
Absolutely.
How do developers actually drive these things? I imagine writing all your deep learning code from scratch in C++.
Oh, man.
Manually instructing the GPU which microscopic cores should multiply which numbers. That would take years.
It would be a nightmare. And that's why we have deep learning frameworks. The textbook uses a perfect analogy here.
The Lego blocks.
Yes, building an AI from scratch is like writing every instruction manually, but deep learning frameworks are like pre-made Lego blocks. They abstract away the painful, low-level calculus and memory management.
So you can just focus on designing the architecture of your neural network.
Exactly.
The text highlights 3 dominant frameworks, and I think it's crucial for you, the listener, to know which tool fits which job.
Absolutely.
First up is TensorFlow, developed by Google. This is framed as the industrial powerhouse. The book mentions it uses a declarative programming style with static computation graphs.
Right.
What does that actually look like in practice?
A static graph means you have to define the entire network blueprint before any actual data flows through it.
So TensorFlow uses static graphs. It's almost like building an entire plumbing system and welding all the pipes shut before you ever turn on the water.
That's a great analogy. Because you weld the pipe shut early, the system can heavily optimize the layout.
Right, so it runs incredibly fast.
Which is why TensorFlow is so efficient for large-scale production, mobile deployment, and getting AI onto edge devices.
Then you have PyTorch, developed by Meta. If TensorFlow is the industrial powerhouse, PyTorch is the researcher's darling.
Yes. It uses dynamic computation graphs.
Right. So to use your plumbing analogy, PyTorch is dynamic. You can literally move the pipes around.
Add valves, change the flow while the water is actively running through it.
That sounds so much more flexible.
It feels much more like standard Python programming, making it highly intuitive. If you have a crazy experimental idea for a new AI architecture, PyTorch lets you test it on the fly.
And finally, there's JAX, also from Google. JAX seems like the high-performance mathematician of the group.
It is. JAX embraces a functional programming style and utilizes something called XLA.
Which stands for Accelerated Linear Algebra.
Right. Think of XLA as a master translator. It takes your high-level mathematical code and compiles it perfectly to run on whatever hardware you have.
CPUs, GPUs, or specialized AI chips called TPUs.
Exactly. It's gaining massive traction for cutting-edge numerical computing.
Here's where it gets really interesting. How do these frameworks handle actual real-world data?
That's the big question.
The textbook walks through an application using the MNIST dataset. For those listening, MNIST is basically the hello world of deep learning. It's a collection of 70,000 grayscale images of handwritten digits, 0 through 9.
When you use a framework like PyTorch or TensorFlow, ingesting those 70,000 images becomes effortless.
Because you obviously can't feed all 70,000 images into the GPU at once.
No, the memory would instantly crash. Instead, the frameworks use built-in tools called data loaders.
Oh, okay.
They automatically shuffle the data and group it into mini batches, say 32 images at a time. The model looks at those 32 images, makes a prediction, calculates its error, and adjusts its weights.
And the frameworks handle all that complex synchronization in the background.
You don't even have to think about it.
Okay, but what happens when the model is just too big? Even with mini batches, some modern models, like the ones behind the chatbots we use every day, are so massive they couldn't possibly fit on the best dedicated GPU.
They couldn't even come close.
Now, instead of picturing a single graphics card, let's picture a massive, humming server farm with thousands of GPUs connected by miles of cable.
That's the reality of modern AI. When a single GPU isn't enough, we have to scale up to multi-GPU environments.
Right.
The textbook outlines 3 distinct strategies for splitting the workload across all these servers. The first is data parallelism.
Okay.
This is used when your model is small enough to fit on one GPU, but your data set is just overwhelmingly huge. You simply clone the exact same model onto every GPU.
But you give each GPU a different chunk of the training data.
Exactly. They process their chunks and then synchronize their findings to update one master model.
But what if the model itself is too fat?
That's where model parallelism comes in.
You literally chop the neural network in half. You put layer 1 on GPU A and layer 2 on GPU B.
Right.
But doesn't that create a huge bottleneck?
Mm-hmm.
The data flows through GPU A and then it has to physically travel over a cable to GPU B before it can continue. Doesn't that cause a massive traffic jam?
It absolutely does. That physical travel introduces high communication overhead. The GPUs end up sitting idle, waiting for data to arrive over the network.
Which defeats the purpose of being so fast.
Right. So for the truly massive models we see today, like the GPT architectures, we use hybrid parallelism.
The holy grail.
But an engineering nightmare. It combines both data and model splits. It requires incredibly complex orchestration to ensure that across a cluster of thousands of GPUs, the exact right pieces of the model are communicating with the exact right chunks of data at the exact right microsecond.
All minimizing idle time. Even with these massive server farms, GPU memory, that VRAM we talked about, is insanely precious. The textbook lists some clever optimization hacks to save memory, and I really want to talk about gradient checkpointing.
Oh, this is a great one.
Normally, during the forward passive training, the GPU saves every intermediate calculation in its memory, so it can easily use them later to learn and update its weights.
But that eats up VRAM.
Right. The text says with gradient checkpointing, you just throw those calculations away to save space and then recompute them on the fly later.
Exactly.
Wait, so you're literally tossing out the AI's short-term memory just to save VRAM, knowing you'll have to do the math all over again. That sounds incredibly inefficient on paper.
It does sound counterintuitive, but it's a brilliant trade-off. Yes, you are trading computation time, forcing the GPU to do the exact same math twice to save storage space.
Yeah?
But computation on a GPU is incredibly fast, whereas running out of memory literally crashes your entire training run.
Ah, I see.
When you're dealing with massive models, VRAM is your hardest limit. Gradient checkpointing lets you train a model that would otherwise be impossible to fit on your hardware.
Wow, okay. And another critical technique mentioned is mixed precision training. Traditionally, neural networks use 32-bit floating point numbers for high-definition math.
Right. But researchers realize that not every calculation needs to be that hyper precise. It's like measuring a recipe.
Sometimes you need the exact gram, and sometimes a rough handful is fine.
Exactly. By mixing in 16-bit numbers where appropriate, you dramatically reduce the memory footprint by half and speed up the computation.
Without losing any noticeable accuracy in the final AI model.
Exactly.
And once the model is trained and ready to actually be deployed, there's Tensority. This is an engine that optimizes the model for inference, which means making real-world predictions.
Right.
Tensority can fuse mathematical layers together and reduce the precision all the way down to 8-bit integers, or INT8.
It's essentially compressing the model. By dropping the precision to INT8, the model can run 3 to 5 times faster without you having to retrain a single thing.
Think of it like compressing a massive 4K video file down to a 1080p file so it streams instantly on your phone.
But the picture quality still looks perfectly fine to the human eye.
That optimization is what allows complex AI to run on-edge devices, like inside an autonomous car or a smart security camera.
Where you need real-time, split-second decisions and cannot afford a delay.
So we've talked about server farms and huge multi-billion parameter models. But I want to pose a scenario to you, the listener. Let's say you're a small business owner or just a curious enthusiast.
Okay.
You want a custom AI that understands your specific medical data or your company's proprietary legal documents.
But you don't have a server farm.
You don't have a supercomputer.
Yeah.
And you definitely don't have a million labeled images to train an AI from scratch. The time and money problem is huge.
This is where we enter the domain of transfer learning. Instead of starting with a blank slate, you take an open source model that has already been trained on millions of generic images or texts by a huge tech company.
For example, a vision model like ResNet 50.
Right. Because it has seen so much data, its bottom layers already know how to identify universal features, basic edges, shadows, curves, and textures.
Right. So you freeze those bottom layers, you lock them so they can't be changed,
Exactly.
and you only train the very top layers of the network to understand your specific task.
Yes.
So you just lock the parts that know how to see basic shapes and only teach the top layers a new medical vocabulary, like identifying a tumor in an X-ray.
Exactly. You save insane amounts of time because the AI already knows how to see. Transfer learning is powerful, but when we deal with modern large language models that have tens of billions of parameters,
Right, the really big ones.
even fine-tuning just the top layers can require immense GPU memory. This is where PFT comes in.
Parameter efficient fine-tuning.
The core philosophy of TFE is, why update 7 billion parameters when you don't have to?
And the crown jewel of PFT is LoRa, or low rank adaptation. I saw this mentioned in the text, but the math seems super abstract. How does it actually work in practice without updating the whole model?
Let's ground this. Think of a massive large language model like a 50-volume encyclopedia.
Okay.
If you want to teach it highly specific medical jargon using traditional fine-tuning, you essentially have to rewrite every single page of that 50-volume set.
That requires massive server farms and incredible memory.
Right. LoRa takes a different approach. It freezes the entire 50-volume encyclopedia. None of the original pages change.
So what does it do?
Instead, it creates a tiny 5-page glossary at the back of the book.
Oh, wow.
Mathematically, it creates 2 tiny sidecar matrices. By multiplying these 2 tiny matrices together, it approximates the massive update you would have normally done.
So by just reading the encyclopedia through the lens of that small glossary, the AI adapts perfectly to your medical data.
Yes. You get the knowledge of a supercomputer, but you're only updating a fraction of a percent of the parameters. The update is so small, you can run it on a high-end gaming PC.
That is a masterclass in linear algebra. You
Yeah.
get the expressiveness of a full model update, but with a memory footprint that actually fits on a consumer graphics card.
Exactly.
Another brilliant PEFT technique the textbook covers is prompt tuning. In this scenario, you again freeze the entire brain of the AI. You don't change its internal weights at all.
Right.
Instead, you add 20 to 100 soft prompts to the very front of your input. The text calls them learnable vectors.
Wait, what is a vector in this context?
Good catch. A vector is essentially just a mathematical list of numbers that gives the AI a specific direction or context.
Okay.
In prompt tuning, these learnable vectors act like a subconscious filter. They guide the AI's behavior and tone for your specific task without altering any of the core model's actual knowledge. So it's literally like giving the AI a permanent sticky note of instructions saying, always answer like a legal professional, right before it processes your question, and you just train the sticky note, not the AI itself.
If we connect this to the bigger picture, these techniques completely change the landscape of artificial intelligence.
They really do.
It means that the barrier to entry has shattered. Anyone, whether you're a small startup, a researcher, or an individual developer working in your basement, can customize massive, state of the art AI models. You no longer need millions of dollars in dedicated hardware to build a highly specialized AI.
So, what does this all mean? Let's look at the journey we've taken today. We started with the biological inspiration of human neurons.
Scaling that up to understand why traditional networks fail at complex spatial tasks.
Leading to convolutional neural networks for images and LSTMs for time. We learned that the sheer parallel math required multiplying all those massive grids of numbers.
Is why we rely on the raw horsepower of GPUs instead of CPUs?
Exactly. We explored how developers actually drive these systems using the Lego-like toolkits of PyTorch and TensorFlow.
The absolute orchestration nightmare of hybrid parallelism on massive server farms.
And finally, the ingenious memory hacks like LoRa and prompt tuning that literally put this massive power right into your hands.
It really is a testament to human ingenuity. We've managed to map the highly abstract concepts of learning and memory onto the strict physical limitations of silicon and electricity.
And every time we hit a physical bottleneck, we find a new, elegant mathematical trick to bypass it.
Exactly.
So to you, the listener, the next time you use a custom AI tool or a snappy app on your phone that recognizes a plan or translates a sign in real time, you now know the intricate, beautiful ballet of hardware and software happening under the hood.
It's not magic.
No, it's matrix math, parallel processing, and incredibly clever optimization.
This raises an important question to think about. We've spent the last decade adapting our software to run perfectly on large, power-hungry GPUs in centralized cloud servers. But as techniques like LoRa and prompt tuning make fine-tuning so incredibly small and memory efficient, what happens when our everyday personal devices, our smartphones and smartwatches, start fine-tuning entirely new AI realities locally in our pockets?
Completely untethered from the cloud.
Exactly. The hardware of tomorrow might make today's massive server farms look like relics.
That is a wild thought to end on. Imagine your phone evolving its own unique AI brain overnight while it charges on your nightstand without ever connecting to a server. Thank you so much for joining us on this deep dive. Keep learning, keep questioning, and we'll see you next time.